Welcome class, myself Professor D.S. Rai, Professor Department of Civil Engineering, BVD ITM Lucknow. Today I am going to discuss KCE 064 Foundation Engineering, in which today I will cover lecture 39, in which we will discuss foundation on reinforced soil beds. References that I have taken: Dr. B.C. Punamiya, Soil Mechanics and Foundation; V.N.S. Murthy, Soil Mechanics and Foundation Engineering; Alam Singh, Soil Mechanics and Foundation Engineering, and some material have been taken from internet. The contents today I will cover: analysis of a strip footing or a reinforced soil bed, analysis of isolated square and rectangular footing on reinforced soil bed, analysis of circular and ring footing or reinforced soil bed, and illustrative example. So, first of all, why it is necessary? Reinforced earth technique in foundation problem. What are the problem we are facing while designing a foundation of a structure? The main problem is weak soil. Weak soil is, and there are many methods by which we can remove these problems. So, the first is existing weak soil is replaced by granular reinforced with horizontal layer of high tensile strength reinforcement to remove the foundation problem. The next is increasing the bearing capacity, reducing differential settlement and net settlement of the foundation, easy construction and obviating deep foundation. So, we can see this is a figure here. This is the foundation here. The earth is reinforced by some reinforcing material, and this is the frame structure resting on the reinforced earth slab. The second is a footing in a closely built up area resting on reinforced earth slab. So, we can see here these are the two buildings. They are built very closely to each other. So, reinforcement is provided throughout the foundation, means including building 1 and building 2. So, we can see here these are the reinforcement provided in the earth to improve the bearing capacity of the soil. The next is, you can see here, this is the isolated footing resting on the reinforced earth slab. So, we here is the reinforcement we have provided over which the isolated footing is rested. The next is a storage water tank. This is the storage water tank, because heavy loads are coming on the earth, means on foundation. So, we have provided a reinforcement bar in a many layers. So, this is the a storage water tank resting on the reinforced earth slab. Now, come to the failure mechanism. What happened? Say, this is the foundation over which loads are coming. See here, this is zone 1 and this is the locus of A dash and A. Between A dash and A, the shear force is maximum, means tau x z, x is the distance and z is the depth of the layer. So, we can see here this is the maximum shear stress plane. So, locus of this point, between the locus of this point there is a maximum shear stress plane. So, here the load will try to move down with respect to the outer zone. The boundary between the downward moving and outward moving zone have been assumed as a locus of the points of the maximum shear stress at every depth z. So, see here, here the earth pressure, this when the load is applied from the top, this portion will try to go outside in both. This is the zone 2 and this is zone 2. Here the reinforcing strips are provided. So, between the A dash and A, the reinforcement will try to push down the reinforcing bar, whereas the remaining portion in zone 2 of both sides of A dash and A, this will try to move upward the reinforcing bar. We can see here this will try to move upward. So, there will be bulkage, try to bulk it out. Now, the next is a shallow foundation on a thin layer of soil with dense reinforcement resting on a rigid boundary. So, here there is a foundation and reinforcement is provided here. This is the width of the footing and this is the U or H, whatever nomenclature we use. So, U by B, if it is more than 2.3, the shear above the reinforcement will look like this way. The whole thing will try to go in upward direction, the foundation, because and there is no any problem in reinforcing bar. So, the next step is when this U by B is less than 2 by 3 and N is less than 2 or 3 or short tie or tie pull out. We can see here when we applied footing on this bed here, the reinforcement with the short tie, So, here this will try to break the reinforcement provided in the foundation. So, shallow and light reinforcement with the short ties here are provided. Now, failure mechanism, another failure mechanism is here we have provided a number of layers, means heavily reinforced the soil and load is applied here. Here U by B is less than 2 by 3. The long tie where N is more than 4, the upper tie here are baked. Now, assumption for the analysis of a strip footing on a reinforced soil bed. At the plane separating the downward and lateral moment, the ties are assumed to undergo two right angle bends around two frictional rollers, and Td is the vertical acting tensile force. The tie soil friction coefficient has been assumed to vary with depth as following equation. So, Fe will be equal to Mf, where M is a mobilization factor, and that will be given by 1 minus Z by B. Z is equal to, here Z is depth of the foundation and B is the width of the foundation, multiplied by 0.7 plus 0.3 for Z by B is less than 1. M is equal to 2 minus Z by B into 0.3 for Z by B is more than 1. So, by this formula we can calculate the this mobilization factor with the different conditions. Now, assumption for analysis of a strip footing or reinforced soil bed. See here, this is the central zone where the load will try to compress the earth beneath the inside the central zone. This is the outer zone, means zone 2 as we have said, and this is the depth of the elements having a height delta H, and the element is A, B, C, D. Here x is equal to x 0. So, x will be equal to L 0. This is the separating plane. Inside the separating zone, the shear stress will be maximum, means this is the line under which the shear tau x z will be the maximum. So, we say here this is the V A D, means force vertical on plane A D, that will be Q 0 into Z. This condition is for unreinforced soil element. Another force is acting upward, that is FAC, this is a B, BC, which depends upon Q 0 Z, and this will act upward direction. Apart from this, one shear force will also act upward, that depend upon Q 0 into Z. So, now come to the element of same nature and same height. Here vertical force on face AD will act downward, and FVC, VBC will act upward. Shear force will act upward, and this is the tension or tight force will act upward. Is it? So, for NR, the number of reinforcement layer provided in foundation soil, the developed tie force has been assumed in the proportion of M is to M2 is to Mn is such that M1 plus M2 plus M3 plus Mn should be equal to 1. Failure has been assumed for various combination of tie pull and tie breakage at a different level. The forces evaluated in the analysis for the same size of footing on the reinforced and unreinforced soil. The elastic theory is applied to estimate the stress distribution inside the soil mass. Now, come to the BCR or pressure ratio. This is a graph between the bearing capacity ratio or pressure ratio Q by Q 0, and this is the U by V. This is the phi degree, that is for 30 degree, 36 degree or 40 degree, 42 degree, like that way. This is the figure we have applied here. So, this is the pressure ratio or bearing capacity ratio. So, bearing capacity ratio improvement is expressed in term of BCR, bearing capacity ratio, or pressure ratio, that will be equal to Q by Q0, where Q is equal to footing pressure on a reinforced foundation, where Q0 is footing pressure on unreinforced foundation, both measured in the same settlement. So, BCR value in mode 1 failure for with the different soil. So, BCR was found in the range of 1.5 to 4 depending on the settlement criteria and density of the reinforcement. So, now come to again the analysis of isolated footing, isolated a square and a rectangular footing. This will also analyze in the same way. We can see here this is the a rectangular footing having this is the Lx, this is the width, this is the Lx, this is the Ly, x, this is the axis x. So, now load is applied Q or Q0 vertically downward. This is the plane of maximum shear force, or this is the zone 2, this is the depth of the reinforcing bar, this is the element at x0 is the point on the plane. So, A, B, C, D is the element where the force will act. Now, come to the VAD means force acting on face AD of the element vertically downward, and upward force of the soil will act upward, that will be FVVC, that depend upon the Q0 and Z. Apart from this, the shear force will also act in this element like this way, then tau xz, and that depend upon Q0 and Z, depth of the element, and AH. Now, this is for the unreinforced element. Now, come to the reinforced element. The same way the VAD, where it is the function of Q and Z for the reinforcing, and for the upward direction force, that is FVBC, that depend upon QZ, and shear force will also act from the side, that will depend upon the QZ and delta H. So, this is the reinforced soil element for the section XX. So, now we can discuss here in the same way in the vertical section like this way. Here again we see here this is the element A, B, C, D again here. This is the y0 instead of x. So, VAD that depend upon Q0 and Z, and this will act downward, whereas FVVC will act upward, that depend upon the Q0 and Z for the unreinforced soil element, and tau maximum will depend upon the Q0 Z into delta H. In the same way, when the soil is reinforced, then the vertical force acting on the top face, that is A, D, act downward, vertical force acting upward, the when it is acting upward when FVBC face VVC, and tau shear force, maximum shear force will act from the side, and this is the TDY. So, we can equate it for the reinforced soil element for the section YY. Now, come to the circular and ring footing. So, with the diagram we can see here, this is a circular footing where the reinforcement are provided in a radial direction and in ring direction. So, we can see here this is the I is equal to 1, 2, 3, 4, 5 and I minus 1 th, that is the M1. So, we can see here J is 1, J is equal to M2 like this way. So, again this is the YY section, here this is the beta inclination from the horizontal at the point Y, I and J. So, this is the element of delta A. So, this is the I, X, I and J. So, this is a figure we have in the circular type of footing. Now, we can discuss here the position. This is the again in the same way as a rectangular and a square footing. Here this is the level 1, level 2, level 3. This is the tau xz, tau xz. This is the different shear force acting at the different level along the x axis. So, like a rectangular and square footing, the same fashion the forces will act on this circular footing. We can see here this is the plan, edge of reinforcement L by 2, L by 2, L by 2. This is the delta H, this is the element we are considering A, B, C, D, x 0. So, here again the same fashion F V D that depend upon q 0 z will act downward on this element, and F V B C that depend upon q 0 z that will act in upward, and shear force will act as q 0 z when the foundation is unreinforced soil. Now, for the reinforced soil again V A D will act downward, V B C will act upward, shear force, maximum shear force will act upward, that depend upon the q into z, and T D x will act upward direction. So, we can see here this is the position. See, this is the maximum shear force that will act at x 0 from the center of the footing, that is a L r by 2, L r by 2, and this is the sigma z, this is tau x z. So, we can see here the tau maximum will act at the center of the and the outer face of the circular fitting, in between the circular fitting. This is the at the x 0. So, now we can go for the pressure settlement curve, and we can see here this is the footing settlement, and BCR we have Q by Q. So, here we can say Q 0 by Q u, the BCR for the reinforcement Q r by Q, and safety S r by S. And the same way this is the unreinforced soil, and we have a pressure settlement curve. So, this is the end. Thank you very much. Thank you.